Betelgeuse or Bugju, a red beast star, is almost there, a cosmic miracle. Accepting that you put it where the Sun is, it would contact the circle of Jupiter. It's colossal, completely unpredictable, and it will explode. Plan for a huge disaster of never-before-seen scale. Betelgeuse, the red Goliath star on the edge of our astronomical framework, is passing frightening messages through space. Cosmologists have found something significantly upsetting about this immense object using the James Webb Space Telescope. Renowned scientist Brian Cox has given an extraordinary rebuke. The inquiry that keeps coming up is, are we going to witness an astronomical blast impact that will change the night sky forever? The conundrum of Betelgeuse in the vastness of the universe is that stars are considered to live and die in surprising ways. Actually, one star has grabbed the attention and concern of both space specialists and the public. Betelgeuse, a red supergiant star in the constellation Orion. It is incredibly massive and old. Its exceptional reddish hue and changing quality have long been fascinating, but recent events have heightened interest in this immense beast. As we learn more about Betelgeuse, we are extremely close to a potentially extraordinary event in its history. But what might these changes in Betelgeuse mean? Are we seeing the beginning of a spectacular cosmic display on an unimaginably large scale? Betelgeuse's tremendous size and life cycle are astounding. It is an eminent giant, approximately 700 times larger than our Sun. Its size is almost beyond human comprehension. Imagine a star so massive that if it replaced our Sun, its surface would extend past Mars' orbit, enveloping Mercury, Venus, Earth, and Mars. This colossal size not only highlights the real significance of Betelgeuse but also reflects its stage in the sublime life cycle. As a red supergiant, Betelgeuse is nearing a dramatic conclusion, expanding and cooling after exhausting the hydrogen in its core and fusing helium. The age and evolution of Betelgeuse are also noteworthy. This star is estimated to be between 8 and 8.5 million years old. While relatively young in human terms, it is ancient in cosmic terms. Over millions of years, Betelgeuse has undergone profound changes, evolving from a hot blue star to the red giant we observe today. It is now in its final stage as a red supergiant. Stars like Betelgeuse change throughout their lives due to the ongoing forces of nuclear fusion and gravity. One characteristic that makes this phase of Betelgeuse stand out is its remarkable reddish color. Its red hue emerges from its cooler surface temperature compared to other stars like our Sun. The Sun's surface is about 5,500 K, while Betelgeuse's surface is around 3,500 K. This cooler temperature allows Betelgeuse to emit light at wavelengths that make it appear red. However, this color is more than just an appearance. It reveals information about the star's physical state and the processes occurring within its vast gaseous volume. Interestingly, Betelgeuse's color has changed over time, adding to its mystery. Historical records from Roman and Chinese times indicate that Betelgeuse was yellow as recently as 2,000 years ago. By the 9th century, Arabic astronomers noted its red hue. This shift over humanity's history is not just a historical reference. It signifies the star's evolution. Fascinating aspect of Betelgeuse is its changing brightness. It is a semi-regular variable star, meaning its brightness fluctuates periodically. These fluctuations have intrigued scientists and astronomers for centuries. Typically, Betelgeuse undergoes a 400-day cycle and a longer 5-year cycle. As early as 1836, Sir John Herschel documented these cycles, and local folklore may go back even further. However, what truly makes Betelgeuse peculiar is not just its brightness changes but their irregularity. Unlike many stars that vary in brightness predictably, Betelgeuse sometimes deviates from this pattern, suggesting complex and poorly understood processes within its enormous structure. Recently, astronomers were shocked by a dramatic and unexpected change in Betelgeuse's appearance. This event, now known as the Great Dimming, occurred in late 2019. Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the constellation Orion, began to dim rapidly. The star was losing its light at an astonishing rate of 0.01 magnitudes per day on average. By February 2020, It was at its dimmest. Typically visible to the naked eye even in areas with significant light pollution, Betelgeuse became noticeably fainter. The mystery of time and light delays complicates observations of Betelgeuse's activities. Because light takes time to reach us, when we observe a star like Betelgeuse, we are not seeing it as it is now but as it was in the past. For Betelgeuse, the light we see today left the star nearly 700 years ago. This delay makes predicting and observing rapid changes in its behavior challenging. Andrea Dupree, the deputy director of the Center for Astrophysics at Harvard and Smithsonian, and her team closely monitored Betelgeuse's radiant display as part of a 3-year study. Using the Hubble Space Telescope, they tracked changes in Betelgeuse's outer atmosphere. These observations provided new insights into how a variable star like Betelgeuse functions. Further analysis revealed that material was moving from Betelgeuse's surface into its environment at about 200,000 miles per hour. This hot, dense material eventually traveled millions of miles from Betelgeuse, forming the dust cloud that caused the star's dimming. The question remains, what does this dimming mean for Betelgeuse's future? Is it a sign of an imminent supernova, or is it a one-time event in the star's complex life? Several theories have been proposed to explain this rapid change. One suggests it is a precursor stage in the supernova process. Another hypothesis posits that dust, possibly ejected from the star itself, obscured our view. It is known that Betelgeuse and other red supergiants shed material, which can accumulate into a dust cloud thick enough to block the star's light. A third hypothesis examined how changes in the star's internal structure, such as convective currents or shock waves within its massive layers, could have contributed to the observed dimming. Regardless of the cause, Betelgeuse's behavior is a captivating subject for astronomers. Its current stage of evolution suggests that it is nearing the end of its life, and a supernova explosion is inevitable, though the exact timing remains uncertain. When Betelgeuse does explode, it will produce an extraordinary cosmic event. The supernova will be so bright that it could rival the moon's brightness and be visible during the day for weeks or even months. The aftermath of such an explosion would be equally fascinating. Betelgeuse would collapse into either a neutron star or a black hole, depending on the remaining mass. The energy released during the supernova would scatter elements like carbon, oxygen, and iron across space, enriching the surrounding interstellar medium and contributing to the formation of new stars and planets. For now, astronomers continue to monitor Betelgeuse closely using ground-based telescopes, space-based observatories like Hubble and the James Webb Space Telescope, and other advanced instruments. These ongoing observations will help scientists better understand the processes leading up to a supernova and the life cycle of massive stars. Betelgeuse serves as a reminder of the dynamic and ever-changing nature of the universe. Whether its dramatic dimming marks the beginning of its end or merely a temporary phase, one thing is certain: this red giant holds secrets that could reshape our understanding of stellar evolution and cosmic phenomena. As we await its ultimate fate, Betelgeuse stands as a cosmic giant on the brink of transformation, a testament to the incredible power and mystery of the stars. In the evident external layer, factors could influence its obvious brilliance. This secret was addressed using a blend of observational techniques and in-depth analysis. Spectroscopic examinations and findings showed that Betelgeuse's powerful temperature had decreased, suggesting that the star might be dimming due to a large dark spot on its surface. The fact that Betelgeuse's temperature decreased by no less than 170 Kelvin around the time of the dimming supported this idea. This demonstrated significant changes on the star's surface. In the end, the Hubble Space Telescope, humanity's sentinel in space, helped us understand this rare event. Hubble's observations revealed that the dimming of Betelgeuse was likely due to a large amount of hot matter being ejected into space. This material formed a dust cloud that obscured part of the star's surface, reducing the amount of light reaching Earth. The dust cloud was believed to consist of very warm plasma that emerged from massive convection cells on the star's surface. As this plasma passed through Betelgeuse's hot atmosphere into cooler outer layers, it formed dust grains that created a cloud, blocking light from about a quarter of the star's surface. The impact of the ejected material was evident from Hubble's ultraviolet spectroscopic assessments, which began in January 2019. These assessments were crucial in understanding the events leading up to Betelgeuse's dimming. They detected dense, warm matter moving through the star's atmosphere months before the darkening. Several ground-based telescopes also observed the star's brightness decrease in December 2019, with Hubble's observations confirming these findings and providing further insights into the ejected material. The discovery that Betelgeuse was losing material at a much faster rate than previously thought led to the realization that this rapid mass loss could impact our understanding of stellar evolution, particularly in red supergiants. It is important to understand that Betelgeuse is not the only star undergoing such dramatic changes. Other historical supernovae, such as SN 1054 and SN 1987A, have provided significant insights into how stars die and how new elements are formed. These past events have helped shape our knowledge of stellar deaths and their impact on the surrounding space. For instance, SN 1987A, which occurred in a neighboring galaxy, offered a close-up view of a supernova explosion and its aftermath. Such supernovae contribute to the cosmic cycle by dispersing heavy elements and influencing star formation. If Betelgeuse were to eventually become a supernova, it would create a spectacular light show visible from Earth. The explosion would be brighter than the Moon and could potentially be seen during the day. Such an event would provide an exciting opportunity to study the final stages of a massive star's life, as well as the development of cosmic structures and the spread of heavy elements across the universe. Despite the dramatic nature of a supernova, the distance between Betelgeuse and Earth provides a safe buffer, ensuring that such an explosion is unlikely to directly harm us. In conclusion, the insights gained from observing Betelgeuse's potential transformation will continue to advance our understanding of stellar evolution and cosmic phenomena. The role of red supergiants in stellar evolution is vital to our interpretation of cosmic development. These stars represent the final stages of a massive star's life cycle before it undergoes a supernova explosion. Their immense size and relatively short lifespans make them exceptional laboratories for studying the end phases of stellar development. Red supergiants play a crucial role in understanding how massive stars evolve and the processes that lead to their explosive deaths. These stars have a significant impact on their surroundings. The energy they release in their final stages contributes to the formation of heavy elements, which are essential for the creation of planets and life as we know it. As we explore the depths of space, stars like Betelgeuse serve as our cosmic window into understanding the universe's most mysterious processes. Betelgeuse's future remains a subject of great scientific interest, especially as we witness the changes occurring on the surface of this giant star. Understanding the behavior of stars like Betelgeuse can help astronomers develop more accurate models of stellar evolution and unravel the fate of individual stars as well as entire planetary systems. A red supergiant like Betelgeuse represents one of the last stages in a star's life cycle. These massive stars burn through their fuel at a staggering rate. Unlike smaller stars such as our Sun, which can last billions of years, red supergiants only survive for a few million years. The sheer size and mass of these stars make their internal processes highly dynamic, and eventually, they succumb to a violent death, a supernova. It is through these violent deaths that red supergiants enrich the universe with heavy elements such as iron, gold, and uranium. These elements are crucial for the formation of planets and, ultimately, life as we know it. In Betelgeuse's case, its core is likely already composed predominantly of iron. This iron core is significant because once it reaches a critical mass, the fusion process within the star will cease. As the core collapses under gravity, it heats up, and the outer layers of the star are violently ejected. This rapid collapse triggers a supernova, an event that sends a shock wave of energy and debris into space. If Betelgeuse does indeed explode, it will not only light up the night sky but also provide invaluable data about the final moments of a massive star's existence. One of the fascinating aspects of Betelgeuse's dimming events is how they could offer clues to the star's internal processes. Typically, stars like Betelgeuse display gradual changes in brightness over time, which are linked to their ongoing life cycle. However, the rapid dimming observed in late 2019 and early 2020 raised alarms among astronomers. The sudden decline in brightness could be the result of a massive ejection of material from the star's outer layers, which formed a dust cloud that partially obscured the star's light. This abrupt drop in brightness could indicate that the star is in the final throes of its existence, with the outer layers shedding significant amounts of mass in preparation for the ultimate explosion. The possibility of a supernova occurring within the next few thousand years remains speculative, but it is an enticing prospect for scientists. Betelgeuse's supernova could have profound implications for our understanding of stellar evolution, as well as how we study such explosions from Earth. A nearby supernova like this would allow astronomers to observe the physical processes involved in a stellar death in real time. The explosion would release a massive amount of energy, including light and neutrinos. By studying these emissions, scientists could gain new insights into the mechanics of supernovae and perhaps even the formation of black holes. Supernovae are not just fascinating because of their dramatic nature. They are also responsible for the creation of heavy elements that form the building blocks of planets and life. When a massive star explodes, it disperses these heavy elements into the surrounding space, enriching the interstellar medium with the raw materials necessary for future generations of stars and planetary systems. These elements, formed in the hearts of dying stars, are the very elements that make up Earth and other planets and are the foundation of the chemical processes that support life. Thus, the death of stars like Betelgeuse plays a fundamental role in the cosmic cycle. The expansion of Betelgeuse's outer layers is another significant aspect of its life cycle. Over the past several decades, astronomers have observed that the star's outer atmosphere is growing in size. As Betelgeuse loses mass, it is shedding material into space while also expanding to enormous proportions. This expansion is a characteristic feature of red supergiants, and it plays a critical role in how these stars interact with their surroundings. The outer layers of the star are primarily composed of hydrogen and helium. As the star expands, the pressure and temperature in its core increase, accelerating the fusion process. The star's outer layers will continue to expand until they reach a critical point, at which time the core will collapse, triggering the supernova.